So go stand there.
I don't think so. Friday, people were planning to go to the office.
Hi Roger, how are you? Sure. Physiological expert. Has nothing to do with me running home. Grabbing something.
Yeah.
It works, right?
It was something weird. It was like breaking up.
Yes, I lowered the resolution for that. It will work. I trust it will work.
Okay.
Just make sure like your sound is off.
My sound is off.
So,
I'm not that stupid.
hi, Mara. I can hear you.
Like all the cool kids are sitting over
Hi, Mara. One second.
But it's like, they're really big.
Can you go stand in front of the camera, Dina? Go stand in front of the camera.
Front of the car?
Yeah. Okay, that's good enough. I just want to see if you show up here.
I did.
I can hear you if you disconnect the speaker.
It's fine. I'm seeing him.
Okay. And can you tell like how many people are watching?
5.
Are you on my neck?
Oh, but there is a delay.
Yeah, there's a delay.
But that's intentional?
He set the delay. There's a delay.
The delay what?
He set the delay. There's a delay. Ahmed, it's working.
But I think it needs to be raised a little bit.
Khalas.
No, just put the book under it.
Not with touching. Not at this time.
Oh. Yeah, عاوزة تطلع.
I'm trying to figure out what this is.
It's got a microphone.
Well, why did you make it? So what's this?
Make sure that
It's just like an old microphone. I think it's a different.
Terry said that she's quick on the draw, and she said that I expected it when she applied.
No, it's not fine. You didn't do as good as job as you could. Whether that was the only
No,
reason.
I didn't. No, I think she was better than me. Seriously.
I think we're all set.
This board is coming?
I don't know actually. I have no clue.
Ross, are you all set? Okay, perfect. Did you get a chance to look at the thesis? Alright, we're waiting for the committee at this point.
What? She's coming? Yeah, but she went to have allowed for us. I'm just watching to make sure it actually works. Sitting down, that's too much work.
Actually, complain about the AC working. I was supposed to try today. It's also too cold today to like.
Still, no.
It's like nice to have. I get it.
It's like
Are you actually live streaming?
No, I can only
Yeah,
imagine.
well, I'm not. He's live streaming.
I felt like the air conditioning never worked in gyms.
no, it never worked. It was part of the,
The HVAC thing.
yeah. We asked Dennis.
It says 2 seconds, but it's
For Dennis, it's actually a good investment.
Yeah, because people stop.
Yeah, because he goes to the
What? Yeah.
He goes to our gym?
now. So.
yeah, he was us actually. Both tournaments, so he probably would have been
Why would he go to, he can go to like literally any gym.
you find that in best people. It's close to the house.
Also, no, if you like are a faculty, if you're like,
You have to pay.
you have to pay to go to the gym.
No,
What? Well, the white one is 5. The left one's going to the white one.
oh, it's incentive.
See the temptation?
Look good.
Yes. So
It's
these
a
yes.
it's a valued product,
These were Costco.
but they don't sell them.
I got like Ahmed and Andrew addicted, but then Costco stopped carrying them. And I just happened to have like a bag left.
Very stuff.
You want to like
We can talk to them.
But they can see. Okay, nice.
And I have Murat on the line.
Good morning, Murat. How are you? You know how this goes.
Yeah, that's what I just said. Oh, yeah, you should like
Time for yourself. Okay.
it's a pretty phrases, and then I get some like names. We have and as you said. Rachel is not.
She has like an upcoming guy.
Yeah.
Yeah, like on the
How's
first
it going?
June.
Sure. Our desk. This is the media desk.
No, I just know what she told me.
Yeah.
That's a
That
big
was
camera.
weird.
Why do you win? Never gonna start on time. It's not gonna start on time. I say we'll start at 5:10, at 10:10.
I've taken it,
My heart is slowly coming to the
Hello.
Hello.
How's it going?
You ready?
What? It'll be fine. Everybody's fine. By the time you get to the stage, it's fine.
Do you think people are watching?
4 people watching. One of them is his parents. Probably, I'm assuming one of his brothers. I don't know the name. I just remember.
No, but do you have any longer know that?
His parents for sure. He's a supervisor.
Yes. That's it.
But he's one of the first guys out here. So.
Yeah.
Oh, maybe.
Random people that ran into
Good morning, everybody. It is that time. So we are assembled, and I happened to get a chance version to see Ahmed's invitation to you all. So I know there's a Game of Thrones theme floating around here. So this is actually GOT, as in Game of Thesis. And Ahmed is about to roll the dice and play the game, and we'll see if he ends up a White Walker or a graduate. But to start with, I'd like to say a few words about our candidate today. So he came to MIT in 2009, coming from Paris. He was from Egypt originally, as you know, but he grew up and spent a lot of time in Paris and going to school there. One thing that I like to do is I like to go down to the archives and dig out the original application essay for said person. You know, when you write the essay to grad school, you think, oh, no one reads this, right? Oh, yes, we do. So, and you'll notice that Ahmed has one word that he likes to use a lot. Okay, so but anyway, amazingly, he hasn't strayed too far from what he wanted to do. He said in his application that he wanted to work in the field of soft matter, and I discovered how research in soft matter is interrelated with fields as diverse as biology and electronics, and we're going to see some electrical work here, as well as combining both fundamentals and applied aspects. And I think that's something true that you'll see in his thesis. Going on, he told us that during his time in Paris, during his time at the French Grande École, that I developed a fondness for physical phenomena and their explanation. I think that's a very French term, to have a fondness for something. We like things that the French have fondness for. Okay. So he spent some time with David Pierret, who many of you know, who's been here to sort of a class from David Pierret, and that really ignited his interest in soft matter. And then he actually did a microfluidics lab with a guy called Charles Baroud, and I don't know if you know this, but he actually was one of those visitors who spent 3 months in my lab when I was at Harvard a long time ago. So there's a connection there. So he came as one of those kind of 3-month visitors. He's gone on to a very successful career there. And then he spent 6 months doing work in Schlumberger on cementing fluids. And Schlumberger is a connection that we've had here over a number of years as well. So he was getting interested in complex fluids more and more and more. And then, of course, in your essay, you transition to trying to sell yourself to the committee, right? So here's the chain. He goes. So he explains that he spent some time in Paris, some time in Egypt. And he says, I possess a cosmopolitan outlook. So, this guy have a cosmopolitan outlook? Yeah, I'd say so. And then again, I have a fondness for discovering new things and new people. So I hope that he spent some time being very fond of new things and new people while he's here, as well as an adaptability to different situations. And I think that certainly summarizes what coming to grad school at MIT is all about. And then he ends with saying, in particular, I find Professor Gareth McKinley's non-Newtonian fluid dynamics program appealing, not fond, but appealing, as it dwells on original phenomena in complex fluids. And so, in this case, it's someone who actually came, saw what they wanted to do, and has really strived to get there. And he says, I want to work more particularly on fluid hydrodynamics. And so you're going to hear a lot of that. But even then, Ahmed was thinking beyond a PhD to what he might do after that. And so he points out, it says, after obtaining my PhD, I would like to pursue further research. I hope to discover something that will be revolutionary in these common but highly sophisticated materials, and which may mark the passage for a new era that I believe is possible by a deeper understanding of such fluids. And he's planning to go to work with a company called 24M, which works on very complicated non-Newtonian fluid, but indeed I think you are going to do exactly what you planned all along. So, coming back to the Ned Stark and Game of Thrones thing, I guess I'll be playing the role of Ned Stark today. And instead of a song of fire and ice, what you're going to hear is a song of electrorheology and carbon black. Amen.
Thank you, Gareth. Thank you all for coming today. I'll be talking over the next 50 minutes about designing devices using electroactive yield stress fluids. And let me start by defining what yield stress fluids are. Yield stress fluids are very common in our daily lives. You see them in materials such as toothpaste, face cream, ketchup, shaving cream. They're basically materials which have a solid-like property, but if you exert some force on them, they will start to flow, like ketchup, for example. they're interesting fluids because to build devices with them because they have they can provide functionality because of that nonlinear aspect of their rheology. The reason they have this nonlinear rheology is that they have an underlying microstructure with elements that interact with each other that give rise to what we're going to call a yield stress. And so when you look at the macro scale, if you and I'm showing here a flow curve, I'm going to be saying this type of curve over the length of the top, where I'm plotting stress versus shear rate. If you take and you're doing a material like water or oil, the slope, it has a constant slope and it's into the viscosity of the fluid. For yield stress materials, you have a yield stress and you have to overcome that stress for the material to start flowing. And we're going to define two types of, the two most common types of models to model these types of material are the big and plastic model, where basically after the flow, it has a constant plastic viscosity, and we can use a more complex model like the Hershey-Blochke model, which has some shear thinning behavior and more complex behavior once the material has yielded. And we're going to be particularly interested in electroactive yield stress fluids. And by that I mean fluids that have some interaction with an electric charge or an electric field. And we're going to be looking at two specific cases of those fluids over the length of the talk. Electrorheological fluids, which are materials which exhibit change their properties from solid to liquid with the application of an electric field. And we're going to be applying them to build small valves for hydraulic robots. And so you can think of this case as basically the low conductivity axis of this spectrum, and where we basically want to control the electrical properties of the material and see a mechanical change. The other fluid we're interested in are carbon black gels, as Garrett said, which are higher in conductivity, and we want to use them for semi-solid flow cells, and I'm going to introduce that concept a little later in the talk. But what we're interested in here, we're going to be doing the converse of what I just mentioned, where we're going to be controlling the mechanical properties of the material and then trying to measure the electrical properties and control them. And so this talk has over the three goals basically for this one. We want to understand the interaction between the electric and the electrical properties of these fluids, and we want to do that through a most experimental characterization of these fluids. Second, we want to develop instrumentation and methods for the characterization and modeling of these materials, and introduce things that will help us gain a deeper understanding of these materials. And finally, we want to link this understanding that we gain at the material level to design rules for devices at the system level, and see how we can inform the design through an understanding of the material properties of those fluids. And so, we're going to be doing this for two distinct classes of fluids, the ER fluids and the carbon black gels, and then we're going to be applying them to robotic ER valves and robotics and flow cells as well. So for the first part of this talk, I'm going to focus on electrorheological fluid characterization. And so, as I mentioned, electrorheological fluids, they're basically non-colloidal suspensions of particles that are about 2 to 5 microns that are in a dielectric medium. And the nice thing about them is they have a reversible liquid to solid change with an electric field. So if you look at this video, when the field is applied, the fluid doesn't flow between the electrodes, and when the field is taken off, is removed, then the material flows, and this behavior is reversible. And the time scale of this effect, it happens on order of milliseconds, so it has a very fast switching time. What it does is that basically develops a field-dependent yield stress in our material. And the reason we have a yield stress here is because when we apply the field, the dielectric particles chain up and form chains that give rise to this yield stress when we apply the field. And as you can see in here in the second video, this shows you that the behavior is reversible, as I mentioned. We're going to study the electrological fluids using two different types of flows. We can look at wall-driven flows, such as torsional rheometers, which are basically the standard for rheology characterization. And to define the term rheology, It's basically the science of how things flow. So we're going to we want to use this type of flow to understand how the fluid flow behavior. On the other hand, we can also look at pressure-driven flows, which are more representative of the applications, such as the valves, but are not as standard and more difficult to implement. So what we ideally would want to do is we want to be able to characterize the materials using a wall-driven flow and apply that to pressure-driven flow, so we don't have to build 100 valves to test the fluids, basically. And so that's what we're going to do. We're going to look at wall-driven flow of ER fluids. And so we built, we're using a torsional rheometer here with a parallel plate geometry, and we're using a custom-made fixture that uses conducting salt to close the circuit and allows us to apply high electric fields on the sample and measure the rheology of the material as we're applying the electric fields. And we're going to be using a commercial fluid called Reoil 4 that has been optimized for commercial use and has a very low current density. And so, as I mentioned, if there's no electric field, the material is Newtonian, and we can see here the flow curve where it's in line, and then we have a viscosity of about 31 millipascal seconds at room temperature. And if we apply an electric field, we basically have a yield stress material where the yield stress depends on the electric field. And we can model it as a Bingham plastic material. And so if we look at the effect of the electric field on the yield stress, we see two things. First of all, that we were able to get yield stress on the orders of about 100 pascal to about 1 or 2 kilopascal, and that the yield stress has a power law dependence of 1/2 with the electric field. When we're higher than 1.5 kilovolts per millimeter. Keep in mind we're applying very high fields here to get this change on the material. If we now then, we basically have modeled we understand the rheology of that material using a wall-driven flow. If we now try to look at a valve and look at the yield stress that we can extract from that pressure-driven flow this time, we see that basically there's a discrepancy between the two, and we're using wall-driven flow, we're underestimating the yield stress, and we don't understand why. And so this is going to be a problem if you want to use rheometers to characterize these materials. So you want to dig a little deeper and try to understand the origin of this effect. And so there are two parameters that control the yield stress of the material. The field is one of them, and I already showed you how that affects the yield stress of the material. The one is the particle volume fraction of the particles in the fluid. And so we went ahead and created a series of fluids of volume fraction varying from 0 to 55%, and we measured again their rheology at a fixed field of 3 kilovolts per mole. And if we now look at the yield stress versus volume fraction, you see, as we expect, that when there's no particles, we don't have a yield stress in the material. And as we increase the volume fraction, the yield stress increases in the material, and initially linearly and then faster than linear when you get to high volume fraction. And we can model this using a modified Krieger-Dougherty model that I'm showing here, and you can see that it is in good agreement with the data that we show. So we understand how both particle volume fraction and electric field affect the rheology in a wall-driven flow. So let's go ahead and look at the effect of, and do the same tests in a pressure-driven flow. So we designed some channels where we can apply an electric field across and visualize at the same time, that you can see here. And we went ahead and tested them. And the way we tested them is we basically pushed the fluid with a syringe at a given volume fraction of fluid, and we watch the pressure rise in the channel. And you can see that initially the pressure rises, and then when basically you reach the yield pressure of the valve, the valve breaks basically, and you can define that as your yield pressure. You can see these oscillations because when the valve breaks, the electric field is still applied, and so the particles chain up again and reform and close the valve again, and then the pressure rises again until you reach the yield pressure again, and that happens over and over and over again. We can do a force balance on an element of fluid in the channel, and we can relate the yield pressure that we measured here to a yield stress in that setup case. And now let's compare for all the volume fractions that we measured earlier, the yield stress in the microchannels for different flow rates and the yield stress that we measured in the wall-driven flow. And you see that for all the volume fractions that we tested, the yield stress in the channel is consistently higher than the yield stress that you measure in the diameter. And the way to think about that is that the diameter is basically a closed system. The amount of particles that are in your measurement are constant, versus in the channel you're introducing particles continuously, and the particle gets stuck, and you get an increase in the volume fraction in the channel. The other thing we notice is that at high volume fractions, we notice a saturation of the yield stress with the volume fraction. And so we can think of this in a way that basically particles get in the channel and get stuck until they reach a maximum packing fraction of about 53% here, phi n. And so we wanted to sort of model this behavior as well, and try to reconcile the differences between the wall-driven flow and the pressure-driven flow. And so we introduce a ratio of time scales in our system. First, T alpha, which is the structure formation time of how the structures are forming, which depends on the electric field, and then a convection time scale, which tells you how fast you're piling particles in your channel if you start from this volume fraction and the max volume fraction is phi n. And we can look at the two extreme cases. You can think of the case where you're applying a very strong flow rate, or and basically the particles don't have time to form, and so you basically end up with no structure in the channel and practically an empty channel. And you can look at the other case where you give the particles enough time to reach an optimal packing in the channel, and in which case you're going to end up with the maximum packing fraction that we discussed here. And so to model this, we take we go through the permeability of this porous media and define the two extremes: the permeability at the maximum packing fraction and the permeability of an empty channel, basically with no particles at all in it. And we basically propose this phenomenological relationship that interpolates between the two using this time scale and an exponential function. And we relate that permeability back to the volume fraction using this relationship that has been demonstrated on this specific fluid using optical measurement by Chen and previously in our lab. And so if we know what the permeability that the material reaches for each ratio of timescales, we can then extract what the volume fraction that forms in the channel is, and then if we know the volume fraction, we can go look on the curve that we characterized on a wall-driven flow to get the yield stress at that point, basically. And you can see here the dotted lines are basically the lines for this set of parameters for our model in the system, and we see that we get good agreement of our model with the data that we collect. And so what we've shown is that we can basically understand the physics in a pressure-driven and wall-driven flows, and we're able to reconcile the differences between the two. And so if we know that the dependence of the yield stress and the volume fraction, we should be able to reconcile data that we collected on the diameter and data that we collected in the channels and do device characterization accurately. For the next few slides, I'm going to go ahead and discuss how we apply these fluids and discuss things at the device scale of things for ER fluids. As I mentioned, we're interested in ER valves, where basically we're flowing this fluid in between in a channel where two of the walls are convective. And you can imagine that we can apply an electric field and the flow will stop, and then if we remove the electric field, the fluid will flow. And that's why they call electrolytic fluids photovalving fluids. And the nice thing about ER valves is that they're basically mechanically simple. There are no moving parts. It's just a pair of electrodes in a spacer. They have a low power. We're using a high voltage, or a high electric field, but the current is very low in the system. They're relatively easy to fabricate because we can make use of existing PCB technology to make the device very small. And as I mentioned, they have a fast switching time because the fluid has a fast switching time. And the other nice thing about them is if you try to build valves for small valves for robotics, what you'll find is that they're very big and very expensive, and so that prohibits the widespread use of small hydraulic robots, basically. Versus ER valves are very versatile and can be made very cheaply if you use PCB technology. And so we investigated, we did some work on the valve design space, and in collaboration with Boston Dynamics, we showed we were able to fabricate, they were able to fabricate valves prototypes using PCB manufacturing methods that you can see here, where you can see these are basically 5 or 6 parallel valves where the fluid is going through, and just the same valve but from a different perspective to give you the sense of scale. We were able to use these valves in designing a small flexible gripper here, made as a tentacle, where basically you have different digits and the NER valve is controlling the flow between each set of the digits, basically, and you can see that you can do precise control of the motion of the gripper, basically, using the ER valves. Okay, and so it's nice because we now are able to use these valves for robotic applications, and there are other examples that I'm happy to discuss. If you want to see more robots that use these things, you can ask me later, and I'm happy to show you. Okay, and so that's what I want to say about the ER fluids. So we were able to characterize them, and we were able to build the valves and characterize their design as well. And so now for the rest of the talk, I'm going to switch to carbon black suspensions and flow cells. And we're going to start with, again, the characterization part of the carbon black and suspensions. But first, I told you that you want to use them for flow cells, but I never told you what a flow cell is. So let me first motivate why we're interested in these materials. Flow cells are basically, it's basically a rechargeable battery that has 2 tanks of it, and you can basically pump the material from the cell back into tanks to store, basically. And this allows you to decouple the energy and the power of the cell, because the power is set by the size of the cell, but you can have a tank as large as you want, and that will control the amount of energy in the cell. So why use flow cells compared to other cells? There's a growing need for grid-scale energy storage because of the increased integration of renewable energy into the grid. As I mentioned, flow cells allow you to decouple the energy and power of the cells, which allows you to have a high power and high energy cell if it's the design process. And it's compatible with a wide range of chemistries, which can be very high energy densities. And so they're promising technology for that reason. And low cost as well. In a typical flow cell, what you do is you flow a Newtonian electrolyte solution through a stationary conductive electrode, such as a carbon felt or porous carbon felt. This can lead to large buffering losses and a very dissipative flow because you're flowing through pores that are very small in the carbon felt. An alternative approach that was shown here at MIT by Professor Chang's group was to, instead of pumping into a stationary electrode, you embed the conductive material directly into the suspension and make a suspension and basically flow the whole thing through the cell. And that's what we're going to call a semi-solid flow cell or suspension-based flow cell. And to do that, we're going to be looking at carbon black gels. They basically are attractive strip particles that are conductive, and they form a related fractal network when you put a large enough volume fraction in your suspension. And they have a very high specific area, which is useful for charge transfer in the cell. And if you look at these pictures, you see that these are not your typical hard spheres suspensions. They're very fractal particles, and they have a short range of attractive potential, and which causes them to basically form gels through a fractal network using diffusion limited aggregation. And so basically we have a fractal network at the scale of the particle and at the scale of the suspension. And so we're going to be using that as a random conductor in the semi-solid flow cells. And we're going to be looking more closely at the lithium sulfur chemistry because it has the potential for high specific energy of the cells, and it also gives you rise to high cell voltage in a non-aqueous solid. And we're going to be looking at, without putting any carbon black into the material, into the suspension, the fluid itself is Newtonian with the active material embedded in it, about 26 millipascal per second of viscosity. And we're going to use our torsional rheometer, a Malvern Pro, that we have enclosed in a glove box to control for oxygen and water to avoid the contamination of our battery slurries with that. And we're using again a parallel plate sinusoidal geometry with a 40 millimeter depth. And so if we look at the flow curves of a suspension made with 1.5% Ketchum black, we see that compared to the curves I showed you earlier, we see this distinctive kink in the curve. And we can go ahead and do the measurement of multiple gaps. If this flow curve is a material property, you would expect that it doesn't matter what gap we're on the measurement at, the flow curve should all overlap, and because it's a material property. When we run the measurements in different gaps, we observe that at low shear rates, the flow curves are gap dependent. This tells us that this and the kink tells us that there is a signature of wall slip in the measurement, and that we have to be careful about how we interpret our data because of that. And so wall slip is common in yield stress fluids and suspensions, and we have to be careful about it. In our case, the suspension is very opaque; it's pitch black. And so we can't do an optical analysis of the slip. So we have to resort to other methods to characterize the slip in our suspension. And so to do that, we're going to use the parallel plate geometry and work done by Yoshimura and Prudhomme and the measurements of multiple gaps to correct for the slip effects in our system. So in the parallel plate geometry, we can write down what the stress at the rim is and the rim shear rate. And as you can see in this figure, we can derive a kinematic relationship between the true shear rate that's applied to the material, the apparent shear rate that we think we're applying to the material, and the slip velocity that's in there. And they're all linked through the gap. And so what we do is for a given stress, we plot that using this kinematic relationship, we plot the apparent shear rate versus the inverse of the gap, and we do this for multiple gaps, and we fit a linear line through. And the slope will be twice our slip velocity, and the intercept will be our true shear rate for that given stress. And here's an example that we did for the 1.5% Ketchum black suspension. And you can see that we get what we expect, basically we can fit linear line through properly. And we can then, the first thing we can get is basically the slip velocity. You can see here I'm applying the slip velocity against the stress, and you see that we get a linear dependence of the slip velocity with stress. But you also see that we have a critical stress below which the material does not slip. And so we can model the slip in the suspension using a slip law that looks like this formula, where basically below the critical stress the material doesn't slip, and above the critical stress it slips is the stress. The idea of critical stress is basically associated with the fact that you need to exert some work to have an adhesive failure at the interface before the material starts slipping. The other thing we can get is the true flow curve of the material, which is plotted in the black here, which is the open symbols that you can see here. And when I overlay the apparent flow curves and different gaps that I've shown you earlier, and you see that we have, when you look at the apparent flow curve, you can see three different regimes that are going to be important for the device layer. Below a stress of about 25 pascals, the material does not slip, it does not flow, there's no flow in the system. Between 25 and 56 pascals, we see that the material is basically slipping, but it has not yielded, and it's basically flowing like a plug. And then when the stress reaches the yield stress, the material then starts to yield, and it can continue slipping as well. And we can fit our data. Fit the data with a Herschel bulking model, and we find good agreement with the data with that model, and somewhat good agreement with the Bingham model as well. And so, what I've shown you is that we can characterize both the rheology and the wall slip of our suspensions on surfaces of interest, and we're going to use that to model the flow in a flow cell. Precisely, and I'm going to show you, and this is what I'm going to show you, where I want to link now the information we've gained at the material level to a system level model to help the design. And specifically, I'm going to be talking about gravity-induced flow cells, which is a new type of flow cell architecture that was introduced here in the Chang lab. We're basically, instead of having what I showed you earlier, pumping the fluid into tanks, we basically have the gravity is the driving mechanism of the cell, and think of it basically as an hourglass where you put the material in one side and then let it flow and then flip the hourglass basically. And so what we want to, and it's nice because we don't have any pumps or things to maintain or things that will break down basically in our system. And these can be made very cheaply and they can be very modular. So it's a promising architecture for semi-solid flow cells. And what we want to do is we want to model the flow in the cell to help to guide the cell design. So if we look at the cell, to give you a sense of how big the lab prototype is, the length of this tank is about 7.5 centimeters. And if we take an element of fluid in the cell, we can do a force balance on it between and derive what the shear stress at the wall is. And you can see that it's basically constant. For a given angle, it's a constant stress that's being imposed at the wall for the material. And so what I'm going to do over the few next slides is I'm going to show you how we can design a semi-solid electrode to fit the needs that we want, and how we can balance the electrochemical constraints and the rheological constraints of the material to make sure that this material can flow through the cell basically. So the first thing we want to do is to design our materials. We want to pick the correct solvent to use. We've been working with the Glyme family. Within the Glyme family, we can pick different glymes of different length of the molecule. And we can see that if we look at the cell discharge for a 0.5% pitch black suspension, that the shorter the diglyme, the better the performance of the cell, and we can reach a higher capacity of the cell. So what that tells us is, from an electrochemical perspective, we want a shorter glyme to get better kinetics and better cell performance. If we now look at the rheology of the material at 0.5% pitch black, we see that the rheology is relatively independent of the choice of the solvent that we have used. And so that tells us that we basically should pick the shortest glyme that we can, which would be diglyme. But the issue with diglyme is it has a very, very high evaporation rate, and so it's hard to operate with. So basically, we're going to pick triglyme as our solvent of choice for testing in the cell. Now that we've picked the solvent, we can now vary the carbon loading. And you can imagine that I can put a lot of carbon and I will have very good electrochemical performance because the conductivity will be high, but the material will probably have a very high yield stress and will not flow. Or I can put very low amount of carbon and it's going to flow nicely, but I will have a very low conductivity and the performance will be poor. So we expect that there's going to be some trade-off between those two parameters in terms of the carbon composition. So if we do the calculation we did earlier for different loadings in carbon black, we can extract the the yield stress of the material, and then plot is an athlete plot where we show the yield stress versus the electronic conductivity of the material. And as I mentioned, what we expect is as we increase the carbon loading, the yield stress increases and the conductivity increases accordingly in our system. And so how are we going to decide what carbon loading we want to use in our cell? As I mentioned, we're going to look at the angle for onset of flow in the cell. The angle below which the material does not flow, will not flow in the cell at all, which is going to be an issue for the cell design. Which is, in the case if you assume no slip, is given by this relationship. This angle is shown in the color code here, and you can see that if you, for example, were to use a 1% catch in black, you basically will, even if you got 90 degrees of the cell will not flow. To help us have a wide range of operating angles, which we're going to define as having flowable angles bigger than 10 degrees, let's say, that makes us choose 0.5% catch in black as our carbon loading of choice. And we can look at the conductivity of the suspension, and it's about 3 millisieverts per centimeter, which is acceptable for cell performance. And so we've picked our gel, which is 2.5 molar lithium polysulfide in triglide with 0.5% catch in black embedded in it. And to do the modeling, as I mentioned, we can use Bingham plastic, which makes for easy flow models in the cell, or we can use the Herschel bucket, which fits our data better, but will make it much harder to derive equations for the flow cell for the flow in the cell. And so, to compromise, what we're going to do is we're going to define a piecewise Bingham plastic model within this range of shear rates that we've measured, and that will allow us to keep the linearity of the model in terms of shear rate, but also get good agreement of the data that we have. And so these are basically the input parameters into the model that we're going to be using. The other thing we want to control is the slip in our system, and we can do measurements of different surfaces. For example, Teflon, which is a high slip surface compared to stainless steel. And when we do this characterization, we can see that, as we expect, that the slip on Teflon is much higher than the slip on stainless steel. And for a 0.5% catch in black solution, it does not slip on stainless steel, but it slips on Teflon. And we can compute the slip law parameters that we're going to be using as the other inputs in our model. And so if you now look at how we're going to model the flow in the cell, we're going to assume that we have a high aspect ratio of the channel, where the width is much bigger than the gap between the electrodes. And as I showed earlier, we're going to have 3 regimes, similar to how the flow curve had 3 regimes. Below, if the stress, we have 2 non-dimensional numbers that are going to control in which regime we're going to be, that are basically tau C star and tau star, that are comparing the stress at the wall to the critical stress to slip and the yield stress. And so if you're below the critical stress to slip, your material will not flow at all. If you're between the critical, if your stress at the wall is between the critical stress and to slip and the yield stress, the material is going to be slipping, and we can derive the relationship with the flow rate in that case. And if the material yields, we're going to have a component that's due to the plastic deformation, a component that's due to slip. And from a design perspective, the ideal case is we want to have a plug-like profile in our velocity, because work previously done by Kyle Smith and his collaborators have shown that maximizes the energy efficiency of the cell. So that tells us we want to be somewhere where tau star is about 0.9 or 0.95, right after the material has yielded, but where it's not only dependent on slip and defects on the surface in that case. And so, using those equations, we can compute the flow time for one pass of the cell. So think of it as basically flipping the hourglass. How long does it take once I flip the hourglass once for the material to flow to the other side? And we can look at the effect of, for example, introducing a slip surface in our device on the flow of our surface. So if we use like the black would be a stainless steel surface and the red a Teflon surface, we see that by enabling the material to slip, we can increase the range of operating angle in our system. If we now look at how this model compares to the experimental data that we measured. The model predicts for 10 degrees, for negative 10 degrees, about 4.9 minutes, and an angle of 11 degrees, 3.2 minutes. So you can see it's very sensitive to the angle right now. And what we observe is about 4 minutes. So the model is able to give us the right range of flow times in the device because we have accurately characterized the rheology in the slip of the material. But overall, if you now look at this curve, ideally you want the flow time from one side to the other to be about 8 hours, 5 to 8 hours to give enough time for the cell to discharge. Right now, if you look at it, we are basically always under an hour for most of the angles, and it's extremely sensitive to the angle. And so we want to slow down that flow rate, so without having to do designs of the cell to figure out which one it is. So using the model, the first thing we can think of to slow the flow rate is to reduce the gap between the electrodes, because there's a nonlinear relationship between the flow rate and that dimension. And if we do that, we can look at changing, so for a Teflon surface, we can look at changing the gap, making it smaller. And what you see is, first of all, for a given angle, yes, it does reduce the time for the material to flow, but it also significantly reduces the range of operating angles consistently. And at the end of the day, within the range of gaps that we would be easy to manufacture, we're still nowhere near where we want to be in terms of time. And so we need to find another solution to slow down the flow in that cell. And the way to do that is to introduce an airflow control element in the cell. So think of a valve or a membrane that slows down the flow of air in the cell, because it's a closed system, and that will basically act as a feedback loop that will slow down the flow of the electrode in the system. And we're going to define the parameter alpha that's basically the flow resistance that represents the flow resistance of that element basically in our system. And if we do the modeling again, which is a little more complex in this case, but doable, we can see that if we change alpha, so the red curve is what we had earlier with no flow, with no element of flow control, we can see that we don't change the range of flowable angles, but we're able to control the flow time significantly up to 500 minutes if we wanted to, basically. And so this tells us that an ideal gift cell will have, we would want to have an airflow control element and slip to basically get to the biggest range of operating angles and control the flow time accurately. And the nice thing is that that element is now an extra design parameter that we can tune to get exactly the flow time we want for a given device. Okay, in the time that's left, I want to discuss a process to measure the conductivity of the suspensions under flow. If you imagine that basically we are flowing this network of carbon black, when it's being sheared, the network will break down and the conductivity will drop consecutively. And so we want to be able to characterize that so we can input it in our models for the performance of the cells and not just rely on the static measurement of the conductivity in that case. And so to do that, we can do measurements of conductivity in DC where we apply a constant potential. I want to emphasize that phi from now on is the potential, not a volume fraction compared to what we had earlier, with confusion. We're short on Greek symbols once we start mixing multiple fields together. We can compute the conductivity in a static case for a parallel plate, or we can do an AC measurement where we apply an AC potential and measure the real and imaginary parts of the impedance. And we can, a typical plot that you might see is a Nyquist plot that shows the imaginary part versus the real part of the system, and depending on the type of conductivity in your system, with ionic, electronic, or a mixed material, you will see different behavior on that plot. And so we can look at who has done measurements of conductivity under flow in the dynamic case, and there are a few measurements, but they're relatively uncommon and tend to rely on strain control rheometers that are relatively rare and very expensive. In general, most of the previous work has focused on very low conductivities that are much less than 1 millisiemens per centimeter, which is not the range we were interested in for the flow cell applications. And so we want to look at basically building a test fixture to do these measurements on a stress control rheometer that we have in the lab. And in the stress control rheometer, the complication gets in it because you have to close the circuit, electrical circuit in the material. And when you're measuring whatever you're connecting to the rotating shaft, it's going to have a high friction that will mess up your rheology measurements. So you will not be able to measure stress and conductivity simultaneously. And so we can look at different methods that have been introduced in the past to do these types of measurements on stress control rheometers. The first way you can think of is just use a gold spring, and it's nice because it's not toxic. It allows you to measure conductivity in AC and in DC, but it has a very high friction because it's solid friction with the shaft. You can think of an ionic solution similar to what we looked at for the ER fluids. It's safe, but it only allows you to measure things in AC because the salt will polarize and you will have a very complicated electrical signature of the salt itself that's going to be hard to decouple from what you're measuring in your sample. And finally, you can think of using liquid metal. What has been used in the past is mercury, like Professor Watanabe, which is definitely low friction and allows for AC and DC measurements, but it's very toxic, and we're certainly not going to do that. And so we came up with an experimental setup to do that. So here is the parallel plate geometry that I showed you, and this is our control stress rheometer. And you see the material sandwiched in between the plates, and the plates are acting as electrodes basically. And we've coated the plates in with a sputtered gold. And the reason for that is when you're doing a conductivity measurement with two electrodes, what you're measuring has a component from the material, which is the bulk resistance, and a component from the contact resistance from the interface, which the contact resistance is basically tells you how easy it is for the electrons to pass through that interface. And so if it's a gold surface, you're reducing the contact resistance of your material. And you are able to measure a material with lower bulk resistance, which means higher conductivity. And finally, we are using a non-toxic liquid metal, which is a indium gallium in the solid trap that provides basically a safe but continuous electrical contact to close the circuit. And we wanted to see how that compares to the existing method that I showed you earlier. So we first did a friction calibration of our setup, and this is just the torque that you get from the setup with no sample in the test fixture for different methods of connecting the rotating shaft. And as you expect, that the liquid metal has a much lower friction than the gold spring. But the nice thing is it's relatively independent of the angular velocity. So it's going to be a very easy correction to do this calibration and correct for it. And so we can look at how that would look on for a calibration Newtonian fluid. So the red curve that you see here is what you would get on a normal rheometer without our setup, and so you see it's a Newtonian material. The blue that you see, the blue lines that you see here is basically the calibration that we did, and you can see that basically the friction of the gallium is about 1 Pascal. If we now measure the calibration fluid using our setup, you get the purple line here. You can see there's a deviation between what you measure with and without the fixture because of the friction. And now if we do the correction by subtracting the liquid metal friction, you see that we're able to recover the correct flow curve of the material. And this tells us that we now have a stress fixture that allows us to do simultaneous measurements of rheology and conductivity as long as we're operating at a stress that's higher than the friction here, which is going to be the case for most suspensions that we're interested in. The other thing we can do is an electrical calibration of the measurement. We want to know how much the setup resistance does the setup have. Again, this is just the setup with no material in the rheometer. And you can see that if you compare a gold spring to the liquid metal, clearly the liquid metal is the winner here because the gold spring has a complicated resistance, dependence of the resistance on the angular velocity, and it's a very noisy measurement as well, so it's going to be hard to get accurate measurements. Versus when we look at the liquid metal, it's a constant DC resistance that's independent of angular velocity, and it's very low. And we can we use a calibration ionic solution from Upton with a conductivity that's within the range that we're interested in measuring, and if we do a contact-resistant calibration correction, we can recover precisely using this setup the conductivity that's reported by the manufacturer. So this obviously we can use this setup to do accurate measurements of the conductivity of the suspensions. And so now let's use it on our carbon black suspensions. And we're now switching to a different type of carbon black that's a simpler system, basically, where we're using PXC72R as our carbon black, which is a carbon black that's been widely studied in the literature, so we can compare our results to other people. And we're putting it just in mineral oil to have a simple system. And this is a model suspension to work on because it does not evaporate, it does not age, and is very nice and well studied before. And so if you now look at, we'll do a simultaneous measurement of stress and conductivity at the same time. And we can see that if we shear the material at 100 over a second, we're able to reach a steady state for both the stress and the conductivity in the measurement. And if we now stop the flow, the stress will go to zero, and you can see that the conductivity recovers as the gel is building up again under static conditions. And the nice thing is, if we now start applying the shearing again, when the material reaches the same values and the system is reversed, the results are reproducible, basically. And you can see if we increase the shear rate to a higher shear rate, we see that the conductivity drops, which is what we expect because the network gets more broken. So we want to look at the steady state curves and try to model the conductivity versus shear relationships that we want to use when we want to try to model this behavior in itself. So we can do the measurements again simultaneously for different gaps. When we're doing a stress strand from a high stress from a stress of 100 Pascal to 0 at certain points, spending 30 seconds per point. And you can see that we get, again, flow curves that are gap dependent, which tells us that there's some slip effects happening with low shear rates. But also you can see when you look at the conductivity that at high stresses, the conductivity decays with stress as we expect. But at low stresses, we see a gap dependence again, which is an indication that we have some contact resistance effects kicking in as well, that we would have to correct. In a parallel plate geometry, the shear rate is inhomogeneous across the gap, across the radius, and we typically use a relationship that looks like this to relate the torque that we measure to the stress at the ring. And we've derived for the first time a similar relationship to correct for the effect of shear inhomogeneity in the parallel plate to compute the conductivity for the shear rate. Similarly, I've shown you how to do a slip correction using a multiple gap method. There's a one-to-one analog for the contact resistance where we can plot the apparent resistivity versus the inverse of the gap, and the slope will be our specific contact resistance, and the intercept will be about the resistivity. And we're going to be doing, to keep the analogy going, we're going to be doing this for each given stress as well. And so the nice thing is now with using this setup, with one simultaneous measurements of relative conductivity at different gaps, we should be able to correct for both the slip and the contact resistance at the same time, which is exactly what we did. And you can see here the black curve is the true flow curve that we get for the material, and you see that we have a complex dependence of the slip velocity, bulk conductivity, and specific contact resistance with stress. And I'm going to walk you through what's happening. If we start at high shear, high stresses, and go down reduce the stress, we basically see that the conductivity, blood conductivity is increasing as the gel is building up because we're applying this small stress. Until this works, until we reach about 60 pascals, and at 60 pascals we see that we have a constant slip velocity with stress, and we basically, which tells us the material is flowing as a plug fundamentally. And we can see the signature of that also because the conductivity, the bulk conductivity does not vary because the material is flowing as a plug and it's not being sheared. And then when we go to very low stresses, we see a very interesting behavior where we see both the contact resistance and the bulk conductivity shoot up, and which tells us that there's some sort of microstructural change that's happening in the material. And we can look at the literature and try to understand what's happening. And previous work done by Vincent Renard and Thibault here shows that for below critical shear rate, the material can form, the carbon black materials can form vorticity line flux, where you can see that basically the material phase separates into these lines here versus the homogeneous case that you can see there. And so we can say that we expect that this electrochemical, this change in the conductivity is a signature of that effect. And because we know they've derived the exact relationship for this exact material of what the difference of the critical shear rate with the gap, we can the points you see in open symbols here are the points where we expect that there is some vorticity line formation happening. You can see that all of those are happening below a stress of about 20 pascals. So this confirms our thoughts that this behavior that we see here is a signature of that effect. And it's also the nice thing about these results is for the first time we're showing that we can decouple the true rheology and the conductivity from the contact resistance and slip. And by doing that, we can gain additional information on how the material is flowing versus if we only had the rheology data, we would not be sure what's going on in this case. And so, going back to the applied side, we initially wanted to use this tool as a characterization tool to help us design our flow electrodes. So if we could, for example, compare different grades of carbon black that are commercial, and they vary by basically the conductivity of their particles and how fractal the particles are. So you can get materials like Keshin black, which is a very high specific surface area, or is made for battery applications, or something like Monarch 120, which doesn't have high surface area. It's basically like a black pigment. And we can compare. We can do our electrical characterization on them, and you can see that there's orders of magnitude difference in the conductivity of these suspensions for the same loading in carbon black. And we also observed two things: the carbon blacks that have a high surface area. VX372R and Keshin black, the black and the red here, we see that they have a high conductivity, but they also have a weak dependence on the shear rate. Like the conductivity does not vary strongly with shear, which means that they're very nice for flow battery applications because we know that we're not going to lose orders of magnitude of conductivity when we're flowing the cell. Now, if you compare this to the other two, which have a low conductivity to begin with, but they also have a very strong dependence with shear that where you can see the conductivity drop by almost an order of magnitude within the same range. Again, they're not meant to be for conductive materials, so we agree with that. And so to conclude, I told you we had three goals when we started this talk. One was to understand the interaction between the electric and the rheological properties of the materials, and we did that for PR fluids and different electric fields and particle volume fractions. And we proposed a model to reconcile the differences that we see between a wall-driven and pressure-driven flows. And we were able to demonstrate that the yield hardening in pressure-driven flow is due to the local increase of volume fraction of the particles in the system, and model that process, the physics of that. We also characterized the rheology and wall slip of the carbon black gels and showed that there are important parameters that we need to take into account when we're modeling the flow in the cells, in the devices. And we looked at the effects of solvent, of how the solvent, the surface properties, or the carbon loading affect these properties in our gels. And as I mentioned, there is a trade-off between the mechanical and electrochemical properties when you're trying to design semi-solid electrodes. So having these characterization methods is very useful to guide your design that way. The other thing we were interested in is to develop new instrumentation and methods to characterize the materials, and we have proposed a new test picture to measure simultaneously the rheologic properties of these gels on stress potentiometers, which has not been done in the past. And we proposed corrections for the first time for both the shear homogeneity and the contact resistance on both for the conductivity under flow, which will allow us to get accurate results in our system. And we showed that basically doing these simultaneous rheologic measurements allow us to get additional information on the behavior of the fluid and guide the cell design and operation basically as a characterization tool. And finally, we investigated the design space of ER valves and their application to hydraulic robots, as I showed earlier, and we applied that, and we applied our understanding of the rheology and the carbon and the slip to the design of a new flow cell architecture, which is the GIF simulation. This demonstrates that having the flow modeling integrated with the mechanical design and the electrochemical design is important for optimizing the flow cell operation. Out of this work, we managed to get a few publications out that I'm showing here for both the ER work that I showed earlier and whatever. If you guys, you can read the thesis or you can look at the papers to get additional information on these subjects. And there are a few more coming that are present in preparation. And I'd like to end the talk by thanking by acknowledgement. First, I want to thank JC and DARPA and project for their funding over the many years I've been here. Then I want to first thank my advisors, Gareth and Becco. Gareth gets to do the introduction. I get to give back at the same time. Working with you guys for the last 7 years has been a true honor. As you saw in my application, when I wanted to come here, I basically was, I'm going to go to MIT if I can get to work with Gareth or Becco. And then when the two of you emailed, they were like, oh, we want to work collaboratively with you. I was like, okay, this is a done deal, basically. I've had a lot of fun working with you guys. Gareth, you've always been driving me to reach a higher standard and be very rigorous in my work. And just talking to you on a constant basis, just you learn so much over such a short time. And Becco, I think there's nobody, everyone at MIT will agree that you are one of the nicest people at MIT. Always supporting us, always there with words of encouragement, no matter how bad our results look or like they show how terribly things are going, and making sure that we don't disappear from grad school or keep the Game of Thrones theme like die. I also want to thank my committee members, Murat and Professor Cheng. It's been challenging bridging the gap between the fields of rheology and the world of electric fields and batteries. I've had a lot. You've taught me so much on those subjects and helped me get to where I am today, understand these materials. And the support you've given me over the years have been tremendous. Next, I want to thank our both the NNF and Team Becco people and all my collaborators who when you spend that much time at MIT, you get to overlap with a lot of people. I had the pleasure of working with you guys and hanging out with you guys. And I want to particularly mention two people. Nadia, who I spent many years as my desk neighbor, who's not here today, unfortunately, but who basically were constantly working together on the AR project. And Thibault, who for over the past year has been a constant source of support and help in mentoring me and trying to understand these systems and getting me to be a better researcher. And as you see, many people have shown up today. Gareth was saying, I hope you get to what I wanted, which is get to meet new people and do new things. And I've had the chance to do that here at MIT, and I was very happy to have done that. I've got through either the work at SP, GradRat, or other volunteer work I've done on campus. In the interest of time, I'm not going to thank every single one on this slide because that will I'm not going to be the one stopping you from getting the cake and assuming it happens. And I want to thank every single one of you, and particularly the people who have been helping me for the last 2 weeks get to this point in time and making sure that I'm eating and surviving and sleeping. And finally, last but not least, I want to thank my family who have, for a really long time, always supported me, always pushed me to do better, and no matter what is happening, are always there for me. And I want to thank them for that. I wouldn't be here without them. And with that, I'm happy to take any questions. Keeping the Game of Thrones.
Yeah, and so we're keeping the Game of Thrones theme alive as well.
I have
guess.
not been able to locate a sword.
And I guess Ahmed mentioned he's been here quite some time. I guess more time than there have been books so far in Game of Thrones. I guess. So, but we won't hold you up until the next book arrives. Okay, so the way defense in mechanical engineering works, we're going to throw this open to questions from the audience now. And so this is an open period of questions for faculty or students. We particularly encourage questions from students. And then there is a period for private question time with the faculty afterwards, and I encourage everybody, faculty and faculty visitors, to stay for additional questions. And then, assuming everything goes well, then indeed there will be a reception in the fluids lab, which is down on the second floor of Building 3. And those of you who don't know where it is, everybody else will show you where that is. So for now, the first part is an open period of questions. I point out that we have one thesis committee member who's online, so you may hear a disembodied voice from the ceiling. But otherwise, please, questions from the audience.
I guess I just have a practical question, not having a lot of experience with device figuring, but these valves that you make, you have to apply a pretty high field to get it to switch states. And could you just give me maybe a rule of thumb, or like what is the power consumption for the switching, and how can you relate to applications like mobile robotics or
Right. So, as I said, you have to put a high voltage, but the current density in the suspensions is 10 to the power -6 microamps per centimeter squared. So overall, in a device of that size, you're like less than a milliwatt of consumption when you're continuously activating the facilities. You can use them for that. I didn't show data for the current, but we've characterized that as well, and shown that there's a lot of parameters that affect the power efficiency of the device, and not just the fluid, but also like what you put between the layers of the PCB and so on. And so there's a bit of that, but overall they're less than a milliwatt for something that is the size of.
Questions? Yes.
Well, that's a question. I work in a very different field, of course, where everything is smaller and smaller. So I was curious about your ER fluids, like how small can you make those valves and channels, and when physics start to break?
We have not tested that. Theoretically, you can make them as small as you can make a PCB. You kind of are limited in that because you want to have enough. The dimension of the channels is probably going to be no less than 100 microns, because otherwise you're going to have particles that will get stuck and jammed in your system. Sort of that's your limit. But in terms of the other dimensions, you can go as big or as small as you want, basically. And yes, it's not as small as integrated photonics or integrated circuits, but if I were to show you, like I said, if I show you a typical hydraulic valve that's considered small, it's like an order or two magnitude bigger in size than that. The fact that you can even get to that right now is impressive in itself.
Additional questions? This is your chance to save him, or the faculty start asking questions.
Postpone it, that's it.
Yeah. No, I do have a question. You mentioned these different Gleim materials. You didn't really say why. What is it that made you focus down on using this Gleim series? And then you did mention something about volatility of them. And so when I look at those, even the diglyme looks like a fairly high molecular mass solvent. So it's surprising to hear you say that it's quite a volatile material.
We initially, the first demonstration of the lithium polysulfide semi-solid suspensions that was done in the chain group by Frank, they used the tetraglyme, and it was a solvent that worked. And they had tried other solvents that didn't work, and so we were basically continuing. We knew that family of solvents gave you good kinetics and good electrochemical performance cycling, so we wanted to stick to what we already knew, basically, and just look at the difference between those three. And the idea was, okay, we knew that it works for tetraglide. Can we get better, basically? And so we tried that. I can tell you that for if you manage to seal the cell completely, the tagline is great. But to give you a sense, when it's a 1 millimeter gap, about 40 millimeter in diameter, I have the vapor pressure number somewhere, but it evaporates within minutes. So as you run the test, you can clearly see the material like disappearing in your cell. That's how fast that disappears. And so for something like the gift cell, we were operating for 8 hours. We were like cautious not to go there, basically, without having to redesign the cell to make it airtight.
Yes.
I was curious, in the flow cell design, why is it important to have it be able to operate at a range of angles? Is that something for the application to grid scale battery storage?
Yes, so depending on how fast you want to get the electricity out, you can change the angles, you can change the charging or discharging rate of the cell.
But you would actually have grid scale battery storage implemented with that
Yes.
type of setup?
So like a motor that would move the angle back and forth, yes, which is energetically could be more favorable than pumping, and also easier to design in the first place.
Well, if there's no other general questions from the audience, then the next stage of this is for us to thank Ahmed once again for his presentation. And I guess you want to leave things?
No, I'm not take
Yes, yeah. And then I'll ask the audience to leave and either hang
Well,
out
we're close
outside